Hi everyone. Uh, After a long time again, I'm preparing a lecture video. So a lot of comments I'm getting like completing this signals and system subject. So almost I have completed all the 4 units. So we are left with only one unit. So I thought of completing it. That is sampling theorem, convolution and correlation related unit. So in fifth unit, two parts are there. But first part is sampling theorem and the second one is convolution and correlation. Convolution already we dealt in third unit because LTI system output is a convolution between input and impulse response, isn't it? So we also solved so many problems, properties also we discussed there, convolution properties and all. So but in convolution and correlation fifth chapter, finding convolution between two different signals using graphical convolution method and using formula like that problems are there. In detail concept is covered there about convolution and correlation properties and correlation concept problem will be there, and also applications of convolution, correlation and all, and sampling theorem. So now let us start the fifth unit, that is the first part in fifth unit, that is sampling theorem. Sampling theorem. So in the very beginning, in the first lecture video, I just said that there is a concept in the signal processing, that is sampling theorem, sampling and quantization, which is a principle involved in converting analog signal to digital signal, isn't it? So here sampling theorem only we are discussing. We are not going for quantization techniques and all. In digital communication subject, quantization techniques will be there. Here sampling theorem is there. Sampling, the term itself is conveying us some information, right? We are going to take samples from the given continuous time signal, because in our subject we are dealing with continuous time signal only. To convert it into discrete signal, we have to take samples. Randomly we cannot take samples, isn't it? After converting it into discrete signal, again we should able to convert it into original signal. Original spectrum we should cover. Original spectrum we got means by applying inverse Fourier transform we can construct original time domain signal also, isn't it? So that's why some criteria has been defined to extract samples or to convert continuous time signal into discrete time signal. So whatever sampling theorem is there in signal processing, that is for band limited signals. That means whatever definition or whatever criteria, whatever principle I am going to discuss now, statement, that sampling theorem statement is valid for band limited signals. That means in frequency domain, the given input signal frequency must be confined to a band of frequencies. Certain maximum frequency component should be there. Beyond that, that signal, the spectrum should not exist. Okay, band is limited, low pass signals. Whatever sampling theorem we are going to discuss, that is for band limited signals or low pass frequency signals. Okay. So just to see the representation, how do we represent continuous time signal x of t? After converting it into discrete domain, how do we represent x of n? So that is a sampling is a principle to convert continuous time signal into discrete signal, isn't it? To convert it into digital signal, again some coding techniques we have to use, like a Manchester coding on binary coding techniques. Different types of coding techniques will be there. That the concept will be there in digital communication subject. Here we are going to discuss only how to convert continuous time signal into discrete time signal, that is extraction of samples. Okay, so here how do we represent a continuous time signal? Always t, continuous time variable on x-axis, amplitude on y-axis. Take randomly any continuous time signal. So if you convert it into discrete signal, x of n ts. Now after that we will replace it with x of n only. But how do we extract? How we are extracting samples to convey that? Starting we represent it as nts, and like this we will extract the samples, isn't it? And like this. So randomly, here one sample, like that we should not extract, right? So here the signal may be defined from plus t1 to minus t1, like that. Randomly we cannot take a sample. Some criteria is there. As I already said, what is the difference between continuous and discrete? In continuous time signal, amplitude will be existing at each and every instant of time. For discrete time signal, it's not like that. Amplitude will be defined only at regular intervals of time. Regular intervals. That means 0. It can be 2 also. Here minus 2. Suppose if it is 1, minus 1, 2, 3, 4, fifth sample, sixth, seventh, eighth. Amplitude cannot be an integer. Amplitude can be anything, integer or non-integer. But on x-axis, we have to take samples at regular intervals of time values, and it must be an integer. Samples are always integers, but amplitude can be anything. It can be a decimal, fractional number, whatever. Okay, rounding of amplitude values is nothing but quantization principle. Okay, so after taking the samples, that means, for example, its corresponding spectrum is, as I already said, we are going to take only band limited signal. Let us say this is a spectrum x of f minus omega to plus omega. This is a spectrum, and we have converted this into discrete time domain signal, and this is also going to have some spectrum, isn't it? Some kind of spectrum will be there, whatever may be, some number of spectrums may be there, like that. So after converting it into discrete time domain signal, whatever spectrum is there, again we should cover original spectrum. Again we have to convert original input signal, continuous time signal. Again we have to convert discrete, we have to get back our original input signal from the converted signal. Perfect reconstruction must be possible. Like that we have to take samples. So original spectrum must be recovered back. Then only that is perfect reconstruction. Okay, so that's why randomly we should not take at regular intervals using some criteria that is given by sampling theorem. Now let us see the statement. Put the heading sampling theorem for band limited signals. Sampling theorem for, please make a note of this point, for band limited, write down the notes, band limited signals. Sampling theorem for band limited signals. Sampling theorem for band limited signals. Okay, put the heading sampling theorem for band limited signals. Sampling theorem. See here. So if any band limited signal having finite energy and band, any band limited signal having finite energy and band limited to omega. That means, for example, let us take, this is our continuous time domain signal x of t, isn't it? X of t. So here, whatever may be the amplitude values and whatever may be the time limit here, plus t1 to t, okay, minus t1 to plus t1, that signal is existing. And what are the assumptions we are taking? This is band limited signal having finite energy and band is limited to omega. That means maximum frequency component of this input signal is omega. Band is limited to omega, or you can take FM also. Any variable you can take. Maximum frequency component of this input signal is omega or omega. That means it has no frequency component greater than omega. Then the signal can be perfectly reconstructed by taking sampling rate, greater than or equal to Nyquist rate. By taking sampling rate greater than or equal to Nyquist rate. So here two different terms have come. Sampling rate, which indicates at what rate we have to extract samples. Okay, at what regular intervals of time, at what frequency, sampling frequency we have to take samples. That must be greater than or equal to Nyquist rate. What is meant by Nyquist rate? Nyquist rate. So here Nyquist rate is defined as twice that of highest frequency component of band limited signal. Okay, Nyquist rate is defined as twice that of highest frequency component of the given input signal. If it is omega, to omega. If it is FM, to FM. So sampling rate, sampling frequency or sampling rate must be chosen as greater than or equal to twice that of maximum frequency component of the signal. This is the principle. Fs must be greater than or equal to 2 omega. Fs must be greater than or equal to 2 omega. Sampling frequency must be greater than or equal to Nyquist rate. Nyquist rate is nothing but twice that of highest frequency component of the band limited signal or given input signal. Okay, So I'll repeat the statement. If any band limited signal, I'm assuming that this is band limited signal. That means its spectrum can be in the manner like its spectrum can be x of f or omega, you can take anything. Band is limited means minus omega to omega. Its band is limited minus omega to omega. Okay, maximum frequency component here is plus omega. So maximum frequency component like this is a spectrum we are assuming for this given arbitrary input signal. Okay, so fs must be greater than or equal to 2 omega. I'll repeat the statement. If any band limited signal having finite energy and band limited to omega, that is it has no frequency component greater than omega, can be perfectly reconstructed by taking the sampling rate greater than or equal to Nyquist rate. By taking the sampling rate greater than or equal to Nyquist rate, where Nyquist rate is defined as twice that of highest frequency component of the given input signal. Okay. So this is a sampling interval. So what I said, sampling interval. Now one more new term I am introducing, right? Sampling interval. Sampling rate means fs. Sampling rate, how do we represent fs? Which is nothing but sampling frequency only. Nothing but sampling frequency. fs is nothing but sampling frequency or sampling rate. Sampling interval means we represent this as ts. Sampling interval is ts 1 by fs. 1 by sampling rate is nothing but sampling interval, we represent it as ts. So just now we said that what is the principle we discussed? fs must be greater than or equal to 2 omega, isn't it? So fs is nothing but, what is the fs here? fs equal to 1 by ts, isn't it? So if I write here 1 by ts must be greater than or equal to 2 omega. Then what about ts? If I take ts here, ts is less than or equal to 1 by 2 omega. 1 by Nyquist rate. 2 omega is nothing but Nyquist rate, isn't it? So that's why here sampling interval must be chosen as 1 by less than or equal to 1 by Nyquist rate. Both are same. Maximum twice that of highest frequency component of the signal. Ts must be less than or equal to 1 by 2 omega, or Ts is less than or equal to 1 by Nyquist rate. Okay. So here a continuous time signal can be completely represented in its samples. One more definition has been mentioned here. A continuous time signal can be completely represented in its samples and recovered back. And a perfect reconstruction, that is nothing but perfect reconstruction, and recovered back if the sampling frequency is greater than or equal to 2 fm or 2 omega. In some textbooks or 2 fm also. If the maximum frequency component we represent using fm means we write it as 2 fm. So a continuous time signal, how do we represent any arbitrary signal? A continuous time signal x of t can be perfectly represented. A continuous time signal x of t can be completely represented in its samples and recovered back if the sampling frequency is greater than or equal to 2 omega, where fs is the sampling frequency. Okay, fs is a sampling frequency and fm or omega is the maximum frequency present in that signal. Proof is very important for this. Analytical proof, graphical proof. Simultaneously I will explain both the proofs. With respect to equations, we will plot the corresponding spectrums and we will discuss the proof in next lecture video. So here two statements I mentioned here. From here, based on this, again I repeat the statement. A continuous time signal can be completely represented in its samples and recovered back if the sampling frequency is greater than or equal to maximum frequency component present in that given input signal. So this is a statement of the sampling frequency. Problems are also there based on this important concept, and problems are very important even in gate level, any competitive exams, and for further coming subjects also, analog communication, digital communication, later on also important sampling frequency concept. Okay. proof and problems next. I'll continue in next lecture videos. Okay, thank you all.